Hey, welcome back to Graph Theory. We're going to start off our work in chapter 6 today. In this lecture, we're going to be talking about an introduction to vertex colorings. So let's just get going right here. We've got the goals in front of you there. What I want to do is I want to motivate with an example, the notion of vertex coloring in a graph. And then I want to tell you about something called the chromatic number in a graph. It's denoted by the Greek letter chi, chi of G. Make another a technical definition, that of a k-critical graph. I want to tell you what that is, and then we'll prove a couple of theorems about k-critical graphs. They're theorem 6.1 and 6.2 in this section, so I'll state them a little bit lower in the theorem, or in the lecture. Sorry. Okay, so let's look at this motivational example. Trying to make this a more applied graph theory lecture here today. So here's the example. I've got 6 math classes listed there: math 240, 343, so on, and the times that they're going to be offered. All right. Maybe I should say this is complete fiction. I'm using HSU course numbers and prefixes to make this fun, but I completely made up these offerings. Some of our courses don't even meet in patterns like this. Okay. But just pretend these 6 fictional math courses are offered at these 6 fictional times. And what is our goal? Well, I'd like to know what's the smallest number of classrooms necessary that I could schedule these rooms with no room conflicts. All right, do I need 6 rooms? Can I get away with 5 rooms? Can I get away with 4 rooms? That's my question. What's the smallest number of classrooms that we could schedule these things? So to model this problem with a graph, let's do it like this. I'm going to denote or denote by the vertices in my graph the classes. So when we model this, each vertex in this graph is going to be a class. There's 6 classes there, and then I'm going to draw an edge between 2 vertices if there's a time conflict. All right, so let me scroll down here. I put the table down so you can see it. So here's what I'm going to try to do. Try to explain what this graph is. So like I've just denoted my 6 math classes by A, B, C, D, E, and F to make it easier to write their labels on the graph. And then let's just check out a couple of the edges in this graph. Yeah. So for example, I've drawn an edge between A and B. A is math 240, B is math 343. And yeah, can you see that on Mondays, for example, math 343 goes from 10 to just short of noon. It's going to conflict with math 240, which starts at 11. So that's why I drew that edge. Okay, that's why I drew that edge. Is because of that conflict. So I'll let you pause the video and check the rest. It'll keep the video shorter if I don't go through every one of those things, but for purposes of continuing here, I'm going to assume that I have correctly shown the edge relations in that graph. I draw an edge between 2 courses if there is a conflict. All right. So now to continue, I'm going to denote by classrooms a label in the graph, or people call these things just colors. So I'm going to give a new notion now. So by a classroom, I'm going to just denote it by a color. And so if I rephrase the question, I'm asking, well, what's the minimum number of colors that I need to color each vertex of that graph? I need to assign each class a classroom, but I want to do it in a way that no 2 classes are in the same room at the same time. So I want no 2 adjacent vertices to get the same color. Yeah, because if I colored 2 adjacent vertices the same color, then I'm trying to put 2 classes in the same room that are happening at the same time. So let's take a look and see if we can't do it. Let me choose some colors here. I think I'm going to start off with red. And well, I can see in this graph right away that, say, the vertices F, C, and B, they form the vertices of a graph that's isomorphic to K3. So they're mutually adjacent. So I need at least 3 colors to color this graph. Yeah. Because those 3 vertices are mutually adjacent. So whatever color I give F, B, and C have to get distinct colors. And because they're also connected, and they're both connected to F. And for that matter, the vertex D is connected to all 3 of those things, and so it needs a distinct color. Yeah, so it's going to take at least 4 colors to do this. If you look at the subgraph generated by F, D, C, and B, that subgraph is a complete graph on 4 vertices. So a complete graph on 4 vertices is going to take 4 colors. Because again, my rule is that if you're adjacent vertices, you can't get the same color. But now I don't think we need any more. Yeah, we don't need any more. I can color that vertex A. The vertex A could get any one of the colors except for green, right? I could make it red, I could make it blue, I could make it yellow. Well, wait, what am I doing? I've got the yellow pen on, I'll make it yellow. Also for E, the only thing I can't color E is red. So why not color E yellow as well? Yeah. So that shows me the answer to the question. The answer to the question is that we need 4 classrooms. We asked for the minimum number, so I won't say we need at least 4. We need at least 4 classrooms for those 6 math classes to have no conflicts, right? So it gives you just one little window into the kinds of problems, scheduling problems, scheduling sporting events, classrooms, network trafficking. Lots of times you want to look at some graph configuration and assign labels, or we'll always call these labels colors. It's more fun, to the vertices in such a way that no 2 adjacent vertices are the same color, get the same label. Cool. Okay, so here's some technical terms. Everywhere here, I've kind of drawn in blue technical terms. I would encourage you to like make a vocabulary flashcard, or if you keep a list of definitions somewhere, because these are the terms that we're getting introduced to in this section. So first is the notion of a K coloring. K is some natural number. And well, I kind of just said what informally a K coloring is an assignment of K colors to the vertices of a graph in such a way that no 2 adjacent vertices get the same color. Okay, so there it is out loud. I tried to write this a little bit more formally mathematically, that if you want something to work with, a K coloring is a function from the vertex set of the graph to the set 1 to K. I think of the set of 1 to K as the colors. Yeah, so it's super exciting of me. I have color 1, color 2, and so on up to color K. But it can't just be any old function. I need it to be the case that whenever 2 vertices are adjacent, whenever they form an edge, then those vertices don't get the same color. Okay, so that's what I mean by a K coloring. I'll call a graph K colorable if it has a K coloring. So for example, if I scroll back up to look at our classroom example, that graph is 4 colorable. I tried to convince you it's not 3 colorable because of those vertices F, D, C, and B. It's also not 2 colorable or 1 colorable. So it's 4 colorable minimally. And that's the last technical term. The chromatic number of a graph is denoted by the Greek letter chi. If you're going to tech it or say it, chi is written like that. Well, in tech, chi is written like that. Chi of G is the chromatic number of G. It's the smallest positive integer K for which the graph is K colorable. All right, so if we go back up here and kind of use our new notation, I didn't give this graph a name. If we call it G, chi of G is 4. Yeah, and I'm making a claim there that that's the smallest number, but while we were filling out the diagram, I convinced you can't 3 color it. You can't, and if you can't 3 color it, you can't 2 color it. Because if you could 2 color something, then certainly you could do it with 3. Just change one of your vertices to a 3rd color. Good. In fact, let's kind of quantify that, or not quantify it. Let's make it sort of one of our rules. This is in a nice box in your book. I wonder if I can make a nice box. Yeah. Now it's in a nice box in our notes too. To show a graph that has a chromatic number K, you can kind of always think of it as a 2-step process. First of all, you have to show that it is impossible to color something with K-1 colors. So you have to show it's not K-1 colorable, and then you have to bust out a K coloring. You have to show you can do it with K. So that's kind of what I did up here. Is I was trying to convince you I can't 3 color that graph because of the vertices F, D, C, and B. So it's not 3 colorable, but I could color it with 4 vertices, so its chromatic number is 4. Okay, it's kind of a standard approach to this. Show something isn't K-1 colorable, and then produce a K coloring. Yeah, oh, here, I keep scrolling back up. I didn't need to. I forgot. I wrote this. Our class scheduled example, the chromatic number of it is 4. Yeah, just what I just said. It's not 3 colorable because of that subgraph from this complete subgraph. If I'm fast enough, that's a K4. It doesn't have a 3 coloring, but we could color it with 4 colors. Nice. I'm talking fast. I talk fast in these things because, well, I'm not really talking to anybody, and I don't want the videos to be long, but you can always slow me down, stop the video. I don't know. Let's look at some examples. I've got some examples here. First of all, this is kind of a trivial example, but K1, you guys know what the graph K1 looks like. It looks like that. It's a vertex with no edges at all. It's the only graph that's one colorable. Well, the only connected graph that's one colorable. A graph chromatic number is 1 if and only if it's trivial. It can't have any edges, because if you have so much as a single edge, that edge has 2 vertices, and that means you're going to need at least 2 colors. Another kind of, I think, easy to see fact is that the chromatic number of the complete graph is n, because in the complete graph, every vertex is adjacent to every other vertex. Yeah. So as soon as you color a vertex, you can't use that color again. It's adjacent to everything, but you have to color every vertex, and so you're going to need at least n colors. I mean, in fact, the chromatic number of any graph is never more than the order of the graph. The complete graph is kind of the worst case scenario. Yeah, everything is connected, so you need all those colors, but you would certainly never need more colors than you have vertices. I'm going to leave this third one as an exercise for you. Maybe it'll show up as a formal exercise. Maybe it's an informal exercise. But a graph has chromatic number 2 if and only if it's not trivial and bipartite. Yeah, it's not trivial and bipartite. Its chromatic number is 2. Okay. Let's do an example where we try to find a chromatic number. So let me give myself some colors. I've got a copy of a graph down here. I've actually got it drawn twice. And I'm just going to start trying to color this thing. So I see in the lower part of this graph, maybe I can show you where I'm looking real quick. I see a K3. That graph has a 3 cycle. So I know right away it's going to take at least 3 colors. Let's make one of them red. There's going to be a lot of this going on. One of them blue and one of them green. You might want to get a box of crayons while we're looking at this section. And now that I've done that, let me start moving around the graph. I can start trying to color some of these other vertices. Let's see. I can color this one green because it's just adjacent to a blue vertex. And now, say, moving around the top, this vertex is not adjacent to anything. I couldn't color it green and I couldn't color it blue. I'm always trying to be minimal here, right? So I had to color it red. But now what about some other vertices here? Well, this one down here in the lower right-hand corner, it can't be red, it can't be blue, but it could be green. Yeah. How about this guy up in the top left? It cannot be green and it cannot be red, but it can be blue. So I've gotten that thing, and now that last vertex, well, it can't be blue and it can't be red and it can't be green. So I have to take a 4th color. I'm going to make it yellow. So what did we just determine here? We just determined that the chromatic number of this graph is no more than 4. Yeah. And my opening comment, I said that it has that subgraph isomorphic to K3. I'll show it to you again. That's the subgraph isomorphic to K3. So I know that the chromatic number is at least 3. Yeah. But there's 2 integers in that interval. So I haven't really determined the chromatic number. And I wonder if some of you are already thinking, as I was doing this, that if I had made some other choices, I wouldn't maybe have been forced to use that 4th color. Sometimes this stuff can be tricky because as I was doing it, you know, I was just kind of looking at neighborhoods and deciding, but it's a complex game. You almost have to be thinking kind of more than one step at a time down the road. So let me just show you that it's possible to 3-color this graph. Maybe you could stop the video and 3-color it yourself, even better. But the story will start the same. That K3 down there is going to require 3 colors. There's no way to avoid it. I have to color those 3 vertices 3 different colors. But now this fourth one, when I went up and chose green, I could have made other choices. I could have made other choices. Let me sort of show you one possible. I'm not claiming it's the only one, but maybe I'd want to color that one red. And now having done that, it kind of forces, this has to be green because it's already adjacent to a red and a blue one. And likewise, this thing down here in the corner, well, I could get away. It could be red. It could be red. And now how about that top left corner? It can't be red, but it can be any of the other two colors. But I want to I don't want to color it blue, because if I color it blue, then I'm going to need a fourth color for that last vertex. But if I color this one green, if I choose green instead of blue, then what does that let me do? That lets me use blue for that last one. And so we've actually found a 3 coloring. So we know that the chromatic number is at least 3 because it has a 3 cycle in it. I've got a 3 coloring, so the chromatic number of this graph is 3. I took this exercise from your book. You can read your author's account from it there, but the moral of it is that graph coloring is a little bit more challenging than just starting at a vertex and kind of trying to do the best you can in its neighborhood all the time, because as you kind of globally start moving around the graph, you can paint yourself into corners that you didn't need to. Yeah, so when I colored that graph the first time, it kind of seemed like that yellow thing was necessary, but by making a different choice early on, I actually could 3 color it. Cool. All right, looks nice. Let's look at another definition, and then we'll get to work proving some theorems and call it a day here. So we're going to call a graph K-critical. It's called K-critical if its chromatic number is K, but you pull any vertex out of it and its chromatic number drops to K-1. So it's K-critical if it needs K colors to be colored, but you take any vertex out and it needs less. Just to point out here that removing a vertex of a graph either doesn't change the chromatic number at all in any graph, or it drops it by 1. And I think the easiest way to see that is if you had some graph that you could color with J colors, well, if you add a vertex to it, it's certainly not going to take more than J+1, right? You've got, it's probably, you could probably do it with J, but if you're willing to give yourself a new color, you could certainly color this new graph. So when you pull a vertex out of a graph, you either don't change its chromatic number at all, or you drop it by 1. A K-critical graph is one where you drop it by 1, and it doesn't matter what vertex you pull out, okay? So here is a little proposition. It's in your book, but it's not called a proposition. I just extracted it out of the text, but it says the following. If you have a graph with chromatic number K, then it has a K-critical subgraph. It must be possible to delete some vertices until you get a K-critical graph. In fact, that's kind of basically going to be the proof, although I'm going to try to prove it formally by induction here. Oops. So here we go. I'm going to induct on the order of the graph. And if the order of the graph is 1, the graph is trivial, its chromatic number is 1, and that is 1 critical. So take the subgraph to be G itself. No problems. So for the induction hypothesis, let's suppose that if you have a graph that has order n, it's at least 1, its chromatic number is K, then we'll suppose that the theorem holds. So any graph of order n greater than or equal to 1 with chromatic number K has a K-critical subgraph. And now give me a graph of order n plus 1 with chromatic number K. Okay, I should have written that there. Let G be a graph of order n plus 1 with chi of G equaling K. All right, good. So, well, if you pull out any vertex and you drop the chromatic number, you do that for any vertex, then G itself is K-critical and we're done. You just take G to be the subgraph and we're done. But if that's not the case, if it's not the case that every vertex removed drops the chromatic number, then there must be some vertex that when you remove it, you don't change the chromatic number. That's just the negation of that, okay? Well, pulling that vertex out has order n. You have an order n graph with chromatic number K, and our induction hypothesis says that that graph has to have a K-critical subgraph. G minus V has to have a K critical subgraph by induction. Well, a subgraph of G minus V is a subgraph of G. So there you go. That proves the proposition. Nice. Before I state the next theorem, let me remind you some notation. We don't use all that much. Lowercase delta of G just denotes the minimum vertex degree in the graph, okay? So lowercase delta G of a graph is the smallest of all of its degree vertices. So here's our first theorem. Oh, we got a bug in my note-taking software here. There we go. Okay. Theorem. It's theorem 6.1 in your text. I'm trying to use so to make good notes. And here's what the theorem says. If you have a K critical graph, then its minimum vertex degree is at least K minus 1. Okay, so it puts a lower bound on the minimum vertex degree of a K critical graph. So I'm going to prove this to you by contradiction. So suppose that we have a K critical graph, but its minimum vertex degree is at most K minus 2. That's just the negation of at least K minus 1. So we got a K critical graph, minimum vertex degree at most K minus 2, and pick a vertex of minimum degree. So let V be some vertex of minimum degree. I don't know that that degree is K minus 2, but I know it's no more than that. Okay. So if G is K critical, its chromatic number is K. And when we pull that vertex out, we drop it by 1. So the chromatic number of G minus V is K minus 1. That's what it means to be K critical. Okay. So let's K minus 1 color the graph G minus V. So we use K minus 1 colors, and we color all of those vertices in G minus V. All right. We do that with K minus 1 colors. No two adjacent vertices have the same color. Now this vertex that we removed in the graph G, it was adjacent to at most K minus 2 vertices. So in this set of K minus 1 colors, at least one of them doesn't occur in the neighborhood of V. Yeah, the neighborhood of V has at most K minus 2 things in it, so it can't use all the K minus 1 colors. At least one color doesn't occur. Let's, I don't know, the author says, suppose it's red. So I'll do the same. At least one color, red, is not in the neighborhood of V. Nobody in the neighborhood of V is colored red, right? So yeah, I'm just saying that again. The neighborhood of V has at most K minus 2 colors. So if we put V back in our graph, we can choose any color that's not in the neighborhood of V and assign V that color, and we will have color G with at most K minus 1 colors, right? Because if you have K minus 1 coloring of G minus V, and you can use one of those to color V, and it's still going to be a coloring because the neighborhood of V doesn't use them all. Well, then we've colored G with K minus 1 colors, but the chromatic number of G was supposed to be K. That's our contradiction. All right. So if you have a K critical graph, the minimum vertex degree is at least K minus 1. So that theorem is really, you could almost call theorem 6.2 a corollary. If you take a graph of chromatic number K, then it has to have at least K vertices of degree at least K minus 1. It's a mouthful. It's a mouthful. G has at least K vertices of degree at least K minus 1. But we can prove it quickly from theorem 6.1. The proof goes like this. If the chromatic number is K, well, then our proposition above says that we have a K critical subgraph. That chromatic number of that subgraph is K because it's K critical. So that subgraph has at least K vertices. Yeah, if it takes K colors, then you have to have at least K vertices. The theorem 6.1 says that if H is K critical, its minimum vertex degree is at least K minus 1. So we've got at least K vertices of at least degree K minus 1 in H. Well, those vertices are also in G. Those edges are also in G. So there you go. You just take the vertex set of H. That's your K vertices that all have degree at least K minus 1. Nice. Talking fast, you can pause. A corollary of this. delta, capital delta of G is the twin of lowercase delta. It's the max vertex degree. And the corollary is an upper bound on the chromatic number. The chromatic number is never any more than the max vertex degree plus 1. Yeah? So how do we prove that? Let's do it by contradiction. If the chromatic number were bigger than delta G plus 1, then the chromatic number minus 1 would be bigger than delta G. That is K, I'm just calling K the chromatic number, minus 1 would be bigger than the max vertex degree. But we just proved that we have vertices. In fact, we have at least K of them, but we have vertices of degree at least K minus 1. So the max vertex degree can't be less than K minus 1. We have vertices of degree K minus 1. So this supposition was a contradiction. Why does a theorem like that all end this video? I hope it's not too long. I'm talking fast. Why do you care? It gives you an upper bound. Upper bounds can kind of be useful. Cycles are graphs in which every vertex has degree 2. So the max vertex degree is 2. So this tells us the chromatic number of a cycle is no more than 3. Likewise, the chromatic number of a path is no more than 3 for the same reason. Paths have max vertex degree 2. What about the wheel? It tells us that the chromatic number of the wheel is no more than the max vertex degree plus 1. Well, that would be n plus 1. That's a completely worthless upper bound in the case of the wheel, because n plus 1 also happens to be the order. So you're not impressed that I'm telling you that the chromatic number is less than or equal to the order, but it gives you an idea of how to use upper bounds. All right, so I'm going to call it quits for that video. Maybe I'll see you in a Zoom meeting on Friday where we can talk about this live. And if not, have a good weekend.